now that we know what inversion is, let's practice it a little bit more. Now, before we practice, let's make sure that we can perform an SN2 reaction. So in all of these, we have bromine as our leaving group, and bromine is known to be a good leaving group. Now for our steric hindrance, we have secondary carbon in this situation, a secondary carbon in this one, and in this one. They're all secondary, so we're fine. For our nucleophile, we have sodium iodide, which is actually a strong nucleophile. We have this methyl sulfur group, and it's even though it's not negatively charged, we have an H over here, a hydrogen. It's still a strong nucleophile, so we can still perform SN2. We have a methylamine, which is also a strong nucleophile despite the fact that nitrogen has no negative charge. Now, we can even look at the neighbors, and we can see that here we only have a primary carbon and a secondary one over here, so there's not too much steric hindrance around. Over here we have a secondary and a secondary, so not too much steric hindrance around. And same thing with this one. We only have secondary carbons around the main carbon, so there's not too much steric hindrance around that. Now, don't take lightly of the neighbor. The neighbor is going to play an important role when it comes to SN2 reactions, especially if it becomes too sterically hindered, then we might not even do an SN2. We might do something else like an E2. Now, let's begin. So for the Fischer projection over here, the one thing to notice is that these are pointing upwards. And so, let me just label that. These are pointing upwards. And if we're going to have an inversion, let's draw the line angle diagram and see what it looks like after we do the inversion and then redraw the Fischer projection. So I'm going to put this middle bond down here in the middle. I'm going to have these two methyl groups going back and up. And so I'm going to draw them right here. And then I'm going to have this bromine and hydrogen facing me. So right here. I'm going to have the two other hydrogens going back. Now, this will look like that. Now, if I have my sodium iodide over here attack from the back side, just like we shown in our regular examples, it will have an inversion where the iodide will be going back, and now the hydrogen that was on this carbon will be going to the front. And so we will get this group. We have our CH3s not moved. We have these two hydrogens are the same. And then we have now our back hydrogen is now on the front as a wedge, and our iodide is going back. Now, if we redraw the Fischer projection for this, it's basically the same thing, but if iodide was on the opposite side. And so, the Fischer projection is this right here. We have CH3 on the top, we have our CH3 on the bottom, our two hydrogens. Now, iodide is on the left side, not the right. And our hydrogen is on the right side instead of the left. And so if you're doing SN2 reaction and you know for a fact it's SN2 on a Fischer projection, you can simply put the nucleophile on the opposite side of where the leaving group originally was. So now it's the same thing for a cyclohexane. Now our two positions for cyclohexane on any carbon is an axial position, which is this position right here, and an equatorial position, which is this one right here for the hydrogen. Now, if a nucleophile is going to attack the backside for our leaving group for this at this carbon, instead of being axial, it's going to be inverted. So what is it going to be? Well, it's going to be an equatorial group. And so your actual answer looks like this, where you have your cyclohexane. You have everything else still intact. For example, this tert-butyl group is going to remain equatorial. And then for our, let me draw this better, for our nucleophile, instead of being axial, it's going to be equatorial. And so we have our sulfur group right here. And the hydrogen, which was originally on it, which looks like this, would force the sulfur to have a positive charge. Now, because of that, this hydrogen is acidic, and so sulfur will get rid of it. And so this will be your nucleophile intact without the hydrogen. And then this hydrogen originally that was equatorial is going to invert and become axial. And so these dashes were not necessary to draw, but I just wanted to show it. And there you go. So this would be your final answer. It would just be the nucleophile inverted. Now with this last one, it's the same thing. We're just looking at the same second example, but from a different perspective. And so if we're looking at it from a way where we can have it as cis or trans with wedges and dashes, you simply do the same thing we did with our regular line angle diagrams. And we would have the methylamine attack from the back side and become a wedge. And so your answer would be the cyclohexane and the methylamine would now be a wedge. And so notice how I got rid of one of the hydrogens, and the reason I did that was because the moment nitrogen has 4 bonds, it will have a positive charge, and so if it has a hydrogen available to lose, it will get rid of that hydrogen as an acid. And so these are your 4 final answers showing your inversion.